Hi, it's Renata here. If it's your first time here, welcome to my channel, The Quanti Girl, where we are going to talk about some topics in applied mathematics, in pure mathematics, in quantitative finance, and in Python program, because I'm a PhD in mathematics and a financial quantitative analyst, and I'm here to share with you some of my experience. When we talk about mathematical models for pricing options, I'm sure that the Black-Scholes model is the most famous model. But as we had talked in a previous video, which link is in the description of this video today, the Black-Scholes model makes some assumptions that are not reasonable in real financial markets. So, if you want to price derivative instruments in a more realistic way, we had talked in the same video that the Heston model has a good advantage over the Black-Scholes model because it introduces uncertainty for the volatility behavior, the volatility of the underlying stock price process. So, as the Heston model is a very interesting model when thinking about pricing options in real financial markets context, today we are going to implement into Python. But before we go to the simulation, I'm going to show you two equations that describes mathematically what is the Heston model. So the first equation is a stochastic differential equation that defines an evolution for the underlying stock price, and the second equation is a stochastic differential equation that defines an evolution for the volatility of the underlying stock price. So now let's go to our simulation. The first thing that you need to do is to import the libraries that we are going to use. So let's import the libraries in the first cell. Let's run it. Now we need to specify some outside parameters. The first one is an initial price for the underlying stock price. We are going to put it as 80. We need to specify a time interval in years. Let's consider only 1 year. We need to specify a risk-free rate. Let's define it as 0.02. We need to specify how many time steps in our simulation. And we need, of course, to specify how many simulations we are going to run. Now, let's go and define parameters for the Heston model. Today, in this simulation, we are not going to calibrate the parameters using data, but we are going to do this in some video in the future. But today, by now, in this simulation here, just accept that we are defining parameters without calibration. One thing that I didn't mention when I showed the two equations defining the evolutions of the Heston model is that we consider a risk-neutral probability measure for the stochastic process, the underlying stock prices and the variance of the underlying stock price. So because of this, we are calling the dynamics of these two processes as risk-neutral dynamics. So let's move on in our definition of the parameters. And the first parameter we are going to define is the rate of mean reversion of variance under this risk-neutral probability measure. The second parameter is a variance long-term mean under risk-neutral dynamics. The third one is the variance in the initial period under this risk-neutral dynamics, we need to specify a correlation between returns and variance under this risk-neutral dynamics, and finally, we need to specify a volatility for the volatility of the underlying stock price, the parameter sigma in the second equation of the two equations that I showed you. So let's run the cell. Okay, now we have our parameters, and now let's move on, and here we define a function for run the simulation of the Heston model. So the parameters of this function are all the parameters we defined previous in this previous cell. One thing here is that for the process defining the evolution of the underlying stock price here, we are going to define it considering the Euler discretization for stochastic differential equations. So you can just make a research about what is Euler discretization for stochastic differential equations. It's basically this form we are considering here. Okay, so let's run the cell that defines the Heston model. And now finally, let's call the simulation of a Heston model. Okay, so here let's plot asset prices and variance over time. Now let's simulate the distribution of the assets price with the varying correlations. So for this we are going to simulate a geometric Brownian motion at the final period. So we have here the asset price density under the Heston model, and let's move on and finally plot the volatility smile of our simulated model, our simulation of the Heston model. So we have here the implied volatility smile for calls in blue and for puts in orange, and that's all. We have the simulation of our implied volatility smile, and with this we can have the prices for our call and put options. That's all for today. Hope you liked the video. Don't forget to hit the like button because it helps me a lot. And also, don't forget to subscribe to the channel so you can watch the next videos. So, see you next time in the next video. Bye!